Chapter 8 is about covalent bonding. Now, covalent, prefix co mean? Yeah, together, right? Like cooperate, operate together. Okay? Coincident, incident, together. Same incident at the same time. So co means together. And valent, what are we talking about? We put valent there. The outside electrons, we're talking about valence electrons. So we're going to put valence electrons together. That's what the name is telling us we're going to do. Okay? So, last unit, we talked about what happened when you put a metal and a non-metal together. The metal gave its electrons to the non-metal. Metals are losers, non-metals are gainers. And they transferred electrons till everybody looked like a noble gas. And then those opposite charges stuck together. That was ionic bonding. And that was an ionic bond. Because it was ions. You made charges, and then the charges stuck together. Then really quickly, because it wasn't that complicated, we talked about what happens when you put two metals together. We said when you put two metals together, they just mix together, and they don't make anything new. We call it an alloy. The gold jewelry you wear is not pure gold. If it's 18 karat, it's 75% gold, 25% other. Okay. But you can buy 14 karat gold, which is 7/12 gold, just over half. Okay. 14/24. Okay. And you can mix it in any proportion. I can't do that with sodium and chlorine. Sodium and chlorine, I got to put one sodium with one chlorine, because each sodium loses one, each chlorine gains one. So I don't really make a compound when I mix metals. I make a compound when I put together a metal and a non-metal. So we've got one combination we haven't talked about yet. And that is, what happens when you put together two non-metals? Non-metals are gainers. They want to fill up their outside energy level. They don't give away electrons. So neither one will give away an electron, so we're not going to be able to do ionic bonding. Got no losers. So they put their valence electrons together. They share their electrons. So the covalent bond is where they share electrons. Okay. So the covalent bond is when they share electrons. Covalent bonding makes molecules. Ionic compounds didn't make molecules, they made formula units. A molecule is specific atoms joined. This atom reacted with that atom and they stayed together. That doesn't happen with ionic compounds. Ionic compounds, you end up with a positive one and a negative one, and all the positives are attracted to all the negatives, and all the negatives are attracted to all the positives, and you can't tell which one gave away the electron and which one took it, where it got it from or where it gave it to. You can't see any of that. So ionic compounds can't do this. We talk about water. That's a specific hydrogen atom hooked to a specific oxygen atom, hooked to another hydrogen atom. All those pieces are connected and they have to stay together as a unit. The sodium gives its electron away. It's got a positive. It doesn't care what negative is next to it. It doesn't have to be the one that it gave the electron to. Now, there's two ways to make molecules. One is a compound, different elements. You make a molecular compound by sharing different elements. So when I make water, hydrogen and oxygen are different from each other, I'm making a compound. The second place you make molecules is actually pretty common in terms of where we see them, but pretty rare in terms of atoms. Okay? There are some atoms that make diatomic molecules. Prefix di. What does the prefix di mean? That'd be hex. That'd be hex, like a hexagon. Die. Two. Like dice, divide. Okay. Die. Yeah, you're thinking dice. Die is the plural of the singular of dice, right? You're thinking about it that way. As a prefix, it means two. So diatomic. Okay. Okay. Yeah, you're thinking about it by itself, but as a prefix, it's a prefix. Okay. Two of the same atom. So the air we breathe is oxygen and nitrogen, but it's not O and N. There are no atoms of O out there by themselves. There's no atoms of N out there by themselves. O always shows up in packets of two. So we breathe O2 and N2. That's what we breathe. We breathe O2 and N2. Okay. So eventually we're going to have to memorize this list. There's 8 of them. Here's the list. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine. This is the hard way. This is the list. It's not the way you want to memorize it. Those are all diatomic molecules. Okay, so they're all diatomic. So I'll give you examples, and those elements always make diatomic molecules. You will never find a hydrogen atom by itself. You always find H2. You will never find an oxygen atom by itself. You always find O2. Well, when you put them together, they don't have to come in twos. H2O is okay. But by themselves, O is O2, H is H2. So that's the list. You can try to memorize it that way. Okay. But go from the names. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, astatine, iodine. Everything that ends in ogen or -ine is on that list. Okay, that's one way to memorize it. That's actually the hard way, because then you have to name everything. The easy way is to think of it, don't think of it as 8. Think of it as 1 and 7. So, well, how is 1 and 7 easier to memorize than 8? Well, let's look and see where they're at on the periodic table. the 1 and 7. It's element number 1, hydrogen, and 7 of them that look like a 7. This is element number 7, nitrogen. Starts at 7. And most of the elements go down column 7. So 1 and 7 is easier to memorize than 8. It's not that bad a list, right? You think 1 and 7? Generine. If it ends in generine, it's diatomic. Okay? So, let's check where we're at. Which of the following can make a molecular compound? How am I supposed to know that? Goes back to here. Covalent bond. 2 nonmetals.
Did they name the elements? Did they define this correlation first?
No. It's actually it's just a random thing that it works. Yeah, it's just random because it doesn't work in 4 other languages. Okay, but which of these could be a molecular compound? Well, what do we want to eliminate? We want to eliminate anything with a metal in it. It's got to be all nonmetals. So C and F are both nonmetals. K and Cr is a metal and a nonmetal. That's out. Na and O is a metal and a nonmetal. It's out. Cr and Ca, a metal and a nonmetal, or 2 metals. So these 2 would make an alloy. This B and C B would make an ionic compound. C wouldn't make anything because krypton's a noble gas. And D would make a molecular compound, molecules, because carbon and fluorine are both nonmetals. Metals, nonmetals. The zigzag line is our friend. So, which of these would be molecular? So, yeah. So that's what we're doing. This is the same decision. It just didn't give you, just didn't separate them. I put them together. Took out the word and. K, metal. Oops. Now CO. Now we've got a problem here. CO is a metal. But they're 2 capital letters, so. Yeah. Okay, Roddy. I enjoy your participating. Let's bring it down to a. Does that make sense? Okay, so see why it's C and O, molecular. How about Al2O3? Well, Al's a metal, this side of the line, so Al's out. NABR, Na, left side of the zigzag line, it's a metal. So the only one that would be molecular would be CO. That's carbon monoxide. That's the poisonous gas that comes out of your heater. Okay. So we've already looked at this piece. When we did the lab before break, we melted stuff. And everything that melted on that pan was a molecular compound. By saying low melting and boiling points, that means that everything, this is what we mean by that, everything that you've ever seen, every pure substance you've ever seen that's a liquid or a gas is molecular. You have never seen a liquid or gas ionic compound. You've only seen ionic compounds as solid or dissolved in water. And they're going to have a molecular formula. We're going to have a formula, H2O. CH4. NF3. Now, there's one slight difference about these formulas and the formulas for the ionic compounds that we wrote before break. Okay? And that is, these don't have to be the lowest ratio. When I put together Al and when I put together calcium and chlorine, calcium makes a 2 plus ion, chlorine makes a 1 minus ion. So I get CaCl2 because that adds up to 0. But I could also get Ca2Cl4 or Ca3Cl6. But these are wrong even though they add up to 0 because they're not the lowest ratio. Ionic compounds have to be the lowest ratio. Molecular compounds don't have to be the lowest ratio. And you know that because you studied them last year in biology class. You talked a lot about glucose. C6H12O6. Right? Spent lots of time talking about glucose. That means 6 carbons, 12 hydrogens, and 6 oxygens are all hooked together somehow. Now, it's not the lowest ratio. Every one of those could be divided by 6, couldn't it? So then I'd write like CH2O, right? But there's actually hundreds of compounds with that lowest ratio. I need to be specific and say, I want the one with 6 carbons, 12 hydrogens, and 6 oxygens. That's glucose, because sucrose, the stuff your white sugar, is C11H22O11. Got that same ratio, CH2O. Fact is, there's a whole bunch of compounds that have that lowest ratio, and they fall into a category of things where they have put water on carbon. See how that's water and carbon? So they've hydrated carbons. They call it a carbohydrate. All your carbohydrates have this lowest ratio. So there's a whole bunch of things that are carbohydrates. Okay? Okay, the formula doesn't tell you how the atoms are arranged. It just tells you how many atoms there are. It doesn't tell me that each one of those carbons was on a separate one of those had it hooked to one of those oxygens. So let's go to basics. The simplest molecule we can make, H2. Okay. That means an H atom with a nucleus and 1 electron, another H, 2 H atoms. Okay. How does H2 form? What happens when 2 H atoms comes towards each other? Well, the nuclei, the positive pieces, they don't want to be next to each other. So these 2 nuclei are not going to run into each other because they've got the same charge. So if I get them close, the nuclei are going to push each other away. But they're attracted to the electrons. The electrons have a negative charge. And they're attracted to their electron and they're attracted to their neighbor's electron. So what they do is they share the electrons. It's holding on to each other's electrons that keep them together. This nuclei hanging on to both electrons, this nuclei hanging to both. So those electrons right there. Oh, let's see how many electrons there are. Right next to this nuclei, there are 2 electrons. If hydrogen had 2 electrons, it would look like helium, a noble gas configuration. And if they share, the other atom is going to have 2 electrons next to it too. The other hydrogen is going to look like helium. By sharing the electrons, both atoms get to look like helium because they get to count both electrons. Noble gas configuration is our answer still. Why does this happen? Noble gas configuration. So we make just nonmetals. Nonmetals hold on to their valence electrons. They're gainers, not losers. They have high ionization energies. It takes a lot of energy to take their electrons off. They can't give away electrons to bond. But they still need to get to noble gas configuration so they'll be stable. And they get that noble gas configuration by sharing electrons with each other. What I mean by sharing does that for us. So here's an example. If you ask my wife how many cars we had, she'd say 2. You ask me how many cars we have, say 2. Do we have 4 cars? Well, we're counting the same cars twice, right? Because we share those cars. We both get to count them. When they share the electrons, they get to count the electrons they share. And they get to count them towards their total, towards noble gas configuration. By sharing, both atoms get to count the electrons towards that stable octet. Everybody wants to look like a noble gas. So both atoms get to count as a total. Okay. So let's show it with electron dots. Electron dot diagrams to show covalent bonding. So and what I'm going to show the covalent bonding of is F2. So first, find fluorine on the periodic table. It's in group 7A. Fluorine has 7 valence electrons. Fluorine gets 7 dots. Okay at that? But it's not F, it's F2. A second fluorine would also have 7 dots. And if I push those two together, what do I get? Well, around this one, there are now 8 valence electrons around that fluorine. It has its stable octet. There's also 8 valence electrons around that fluorine. I'm counting the same electrons twice. covalent. Their valence electrons are together. And if everybody looks like a noble gas, we're at low energy, things are going to stay the way they are for a while. They're stable. So by sharing electrons, they both end up with full orbitals, both end up with full energy levels, both end up looking like noble gases, all of those things. That fluorine has 8 valence electrons, and that one has 8 valence electrons. 8 valence electrons, 8 valence electrons. So last chapter we moved electrons to make bonds. Now we move the whole atom to make bonds. What I just drew there was a single covalent bond, a sharing of 2 valence electrons. Okay, it's going to happen with nonmetals and hydrogen. This is just a reminder that we have to decide, our first decision is which kind of bonding is it? Is it ionic, where they transfer electrons, or is it covalent, where they share electrons? So first I have to decide, how are these going to hook to each other? No, more than one moment. Yeah. Okay, different from ionic because these form molecules. Those 2 F's stay together. Because if you try to take those 2 F's away from each other, they no longer have noble gas configuration. 2 specific atoms are joined. That F and that F, those 2 F's have to stay together the whole time if everybody's going to look like a noble gas. Versus an ionic solid, where you can't tell which atom the electrons move to or from. So if I remember, sodium chloride was alternating positives and negatives. This negative picked up an electron from someplace. Can you tell which one of the positives it picked it up from? Does it have to stick with the positive it gave it to? Where did it got positive it came from? They don't have to stick together. They're not a molecule. The 2 F's stuck together. They have to stay together the whole time. If I tried to move one of them, I'd break the noble gas configuration. If I move this, take this negative out, everything here still has noble gas configuration. So ionic compounds make formula units. Molecular compounds make molecules. Okay, so now it's time to start drawing some of those dot pictures to show how they're formed. Now, the process is different than doing ionic compounds. Ionic compounds, you followed the dots until everybody was happy. Here, the process is like a jigsaw puzzle. What is the most useful part of a jigsaw puzzle? What? Everybody wants to say the sides or the corners. I'm going to say the picture on the box. Everybody agree that it's pretty handy to have the picture on the box, to know what it's supposed to look like when you're done. Well, that's how this is like a jigsaw puzzle. I have to tell you what the final formula is. Last unit I could say, put together calcium and chlorine, and you would figure out that it took 2 chlorines for each calcium. Here I can't say to put together carbon and hydrogen, because I can put carbon and hydrogen, just those 2 elements together, in millions of ways. I can't just tell you to put together carbon and hydrogen, because you can make CH4, C2H6, C3H8, C3H6. Lots of different ways to put together carbon and hydrogen. So I have to tell you which one I want. I got to tell you what the picture on the box looks like. And then you just have to put together the pieces, the dot diagrams, until you end up with the right formula. So I've used an example before, so let's go ahead and draw it. Show me how water is formed with covalent bonds. And the picture on the box for water is H2O. That's what I need to make it look like. So look at the box, I need to make it look like H2O. So I open up the box and I look at the pieces. And the pieces I have are the electron dot diagrams. Hydrogen gets 1 dot. Oxygen, group 6A, gets 6 dots. Those are my pieces. Here's my box. Okay, so hydrogen has 1 valence electron, but one of the things it's going to get used to is thinking about what they, not just how many dots they have, but how many holes they need to have filled. How many more electrons does hydrogen need before it's going to look like a noble gas? Hydrogen's here. How many more electrons before it looks like a noble gas? 1. Hydrogen's number 1. Helium's number 2. So why don't you go ahead and turn that off and give it to me, please? I'm speaking to you, yeah. Okay. He only wants 1 more, because if he gets 1 more, it looks like helium, a noble gas. Oxygen has 6 valence electrons. I knew it had 6 because it was in group 6A. So we got our 6 dots. But also handy to think about it is how many holes it needs to have filled. So it's got 1 there and 1 there. 2 more would make it look like a noble gas. That's why we said oxygen always made a 2- ion. Now it's not going to make an ion, but it's still going to need those 2 electrons. It wants 2 more. So they share in order to make each other happy. So there's my pieces. I stick together an H and an O. The hydrogen's happy. It's got a pair of electrons. It looks like helium. The oxygen's not happy. It still wants one more. Well, luckily for us, the box doesn't say HO. It says H2O. I've got another piece to put in. So I put in that second hydrogen. And now the second hydrogen looks like helium. It's got 2 dots next to it. And the oxygen has a full octet. Everybody's full. Everybody looks like a noble gas. We're done. My picture looks like the picture on the box. I got 2 H's and an O, and everybody looks like a noble gas, so they're all connected together. Ta-da. Extra hard? Sometimes atoms have to share more than one pair of valence electrons. One pair is not enough. A double bond, a single bond was sharing 1 pair. A double bond is sharing 2 pair. And 2 pair means 4. A triple bond, sharing 3 pair. There is no quadruple bond. So the single, double, triple refers to pairs. Single 1 pair, double 2 pair, triple 3 pair. Be careful when you read the question. Does it ask for electrons? Does it ask for pairs of electrons? Those get you different answers. Okay. And we use multiple bonds when one's not enough. We try one, it doesn't work. I mean, isn't that how you do a jigsaw puzzle? You try a piece and it doesn't fit, so you go get another piece. It's trial and error. So the technique we're using here is called trial and error. We try pieces and see if they fit. Okay, so what am I talking about here? Carbon dioxide. Anybody ever heard of carbon dioxide before? Huh? Well, its formula is CO2. Notice how the di fits in? Carbon dioxide, carbon to oxygen. Okay. Now I'm going to tell you carbon's in the center. For right now, I have to tell you. Later on, you'll be able to figure out what goes in the middle. But carbon is going to be in the center. That means the 2 oxygens have to hook to carbon. So CO2, that's my picture on the box. My pieces, C, carbon has 4 valence electrons, has 4 holes it needs filled. And carbon had 4 dots because it was in group 4A, 1 dot on each side. No pair up until they have to. Oxygen, group 6A, 6 dots. And it only has 2 holes to fill before it gets to 8. Stable octet. So those are our pieces, and here's our picture. So let's try to build the jigsaw puzzle. So I put the carbon and oxygen together. Did that solve any problems? Well, the oxygen, if I look at the oxygen, it's got 7 around it, not 8. And the carbon only has 5. So putting those two pieces together did not complete the puzzle for me. But that's luckily for me, because they told me the formula wasn't CO, it was CO2. So I had to put another O on. And I know the second O has to attach to the carbon because it told me carbon was the central atom. That solve any of my problems? Well, this oxygen still has a hole. This carbon has 2 holes. This oxygen still has a hole.
Can't the carbon, like the top holes, merge with the top hole?
Yep.
Bottom hole?
Yep. So you're right with me. It's not so much holes as we want to share more electrons. So we tried making single bonds. We put everything together with our single bonds, and it didn't work. It didn't make anything happy. And there's no way I can move pieces around so that they're going to be happy. My only solution is to share more electrons. So don't think about it as holes, but think about it as sharing more. I'm going to take 1 from each. Take an electron from each one and make another bond. See that again? That's where I was at. Take 1 from each, erase it, and put it there in between the 2. Say, well, what good does that do? Well, everybody gets to count all the shared ones. Since they're sharing all of those, how many dots does that oxygen have next to it now? It's got the 8 that I wanted. Has it solved all my problems? Now, carbon still got a hole. This oxygen still has a hole. Ah, if it worked well the first time, let's do it again. So I do the same thing on the other end. Take 1 from each and make another bond. So if I count this, this is 1, 2, 3, 4 bonds. 2 double bonds. And each atom gets to count all the electrons in the bond. So that carbon, with the carbon, look at the dots next to it. The carbon's got 8 dots next to it. This oxygen has 8 dots. That oxygen has 8 dots. Hey, tonight's homework is not going to have you do this. It's going to be reading about it, seeing where we're going with it.